Hello class, I hope you're having a wonderful day. Today I would like to complete a practice problem from chapter 5 that goes over inclined planes. And I'm going to read the problem to you, underline some important information. Then I'm going to generate a column of knowns and then I will draw a picture. So let's go ahead and get started. A 14.4 kilogram wooden box is placed on a metal incline in a manufacturing facility to slide down to the level below. The inclined plane is at an angle of 38 degrees from the horizontal. The coefficient of kinetic friction between the box and the inclined plane is 0.519. The height of the metal ramp is 3.66 meters. Draw a diagram and we are going to calculate the 8 items. So let's first generate a column of knowns. So let's pull information out of the problem that the problem gave us that we're going to need to solve this problem. So the mass of the box is 14.4 kilograms and angle theta between the inclined plane and the horizontal is 38 degrees. And we also have a coefficient of kinetic friction, and this is identified by mu sub k. This is 0.519. And the height of the metal ramp is 3.66 meters. Okay, with this information, let's go ahead and draw a simple picture. Now, the first thing I want to do is we're going to calculate the length of the inclined plane, and this is going to be our hypotenuse value. So, okay, we've got something that looks like this. And it tells us that the height of the inclined plane is 3.66 meters. And it wants to know the length of the inclined plane. That's part A. Now, some important information here. Angle theta is equal to 38 degrees. So we want this dimension here, the length of the inclined plane. Now, we have an opposite side length with respect to angle theta of 3.66 meters. So what we can do is we can start out with the base equation. Sine theta equals the opposite side length divided by the hypotenuse. And so I'm going to adapt this equation to my situation. I'm going to be a little bit more specific with my variables, opposite and hypotenuse side length. So I'm going to say sine theta is equal to the height of the inclined plane divided by the length of the inclined plane. Okay? Now our unknown is on the right-hand side of the equal sign in the denominator, and this is what we want to isolate. So the first step I'm going to do is multiply both sides of the equal sign by length of the inclined plane. Okay, on the right-hand side of the equal sign, it cancels. So I have length of the inclined plane times sine of the angle theta is equal to the height of the inclined plane. Now I'm going to divide both sides by sine theta. And this is going to give me length of the inclined plane is equal to the height of the inclined plane divided by sine of the angle theta. Okay? So the height, the problem tells us the height of the ramp is 3.66 meters. And we're going to take sine of the angle theta. Angle theta is between the inclined plane and the horizontal, and this is 38 degrees. Okay, so go ahead and take out your calculator. Make sure your calculator is in degree mode. So 3.66 divided by sine of 38 degrees. This is going to be 7.8 meters. Okay, let's transfer this value right over here for part A, 7.8 meters. Okay, now the problem wants us to calculate the weight force due to gravity. We know that weight force due to gravity is identified by F sub g, and this is going to be the product of the object's mass and the acceleration due to gravity. So mass times gravity, this is going to be 14.4 kilograms times negative 9.8 meters per second squared. So on our calculator, 14.4 times negative 9.8, this gives me a negative 141.12 newtons. And so looking at our units here, we have a kilogram times a meter divided by second squared. And we know 1 kilogram meter per second squared is equal to 1 newton. So let's transfer this value over here. Okay, and since we have some information written down in part A and part B, what I'm going to do is kind of clean this up a little bit. So let's go ahead and erase a little bit of this so we can finish our problem. Okay, so we have our crate, and remember the first rule, or the first fact for the 6 facts for an object on an inclined plane: the weight force vector points in a negative y direction and it is perpendicular to the horizontal. So we have a 90-degree angle there. The weight force is identified by F sub g, and we calculated that to be negative 141.12. So I have my vector arrow pointing in the negative y direction, showing me the direction is negative y, so 141.12 newtons. And since our crate is on an inclined plane, we know that we can use vector resolution to break that weight force vector down into its x and its y components. And the angle between the weight force due to gravity and the y component of weight force is equal to the angle between the inclined plane and the horizontal. So this angle here, we have 38 degrees. This is our y component of weight force, and we know that it is perpendicular to the inclined plane. And we know that our x component points down the inclined plane, and it is parallel to the surface of the inclined plane. It is identified by F sub g sub x, and we can project this vector down here. And we're using the head to tail method, so we're going to place the tail of the x component of weight force vector on the head of the y component of weight force vector. So right here we have F sub g sub x, okay? And we know that this right here is a 90-degree angle. So our problem in part C wants us to calculate the x component of weight force. So this side length is opposite to our 38-degree angle. So we could start out with sine theta is equal to opposite side divided by the hypotenuse side. So sine theta is equal to, my opposite side length is the x component of weight force, and then we're going to divide that by the hypotenuse, which is weight force due to gravity. Solving for the x component of weight force, I have weight force due to gravity, which is a negative 141.12 newtons times sine of 38 degrees. And this is going to give me 86.8. So negative 86.8 newtons. And our negative is showing direction. So our x component here is pointing in the negative x direction. So negative 86.8 newtons is the answer for part C. Now let's take a look at part D, the y component of weight force. So this side, with respect to that angle 38 degrees, is the adjacent side length. So that means we're going to use cosine. So cosine theta is going to be equal to the y component of weight force divided by weight force due to gravity. So we're going to isolate this guy by multiplying by the weight force due to gravity on both sides of the equal sign. So this gives me y component of weight force is equal to negative 141.12 newtons times cosine of 38 degrees. So on our calculator, I get 111.1, so negative 111.1 newtons. And this is the y component of weight force. And just to remind you, we have a negative sign here because our vector arrow for the y component of weight force is pointing in a negative y direction. So let's go over here to our list of answers. Negative 111.1 newtons. Now, we need to calculate the kinetic friction force. So, before we do that, let's go ahead and write down the equation for the coefficient of kinetic friction. So we know that that is mu sub k, and this is equal to the kinetic friction force divided by the normal force applied to the object. So we know the kinetic coefficient of friction. It's given to us right here, 0.519, and the normal force, we need to go ahead and calculate that before we solve for the kinetic friction force. We know that the normal force is equal in magnitude to the y component of weight force, but opposite in direction. So F sub n, normal force, is equal to 111.1 newtons. And this normal force applied to the crate will put our crate in equilibrium in the y direction, okay? So, right here, we're going to isolate this guy. I'm going to multiply both sides of the equal sign by normal force. So, the kinetic friction force is equal to the coefficient of kinetic friction, which is 0.519, multiplied by the normal force, 111.1 newtons, and this is going to give me 57.7 newtons, okay? And if you notice, this vector is positive. So, right here, when we draw our vector, it's pointing in a positive x direction. Remember that friction always opposes motion. So, kinetic friction force, 57.7 newtons, okay? Now, in part F, it's wanting us to calculate the net force applied to the object. So, the net force in the y direction, we see that the normal force applied to the crate is 111.1 newtons, and the y component of weight force, so the weight pointing into the ramp, is negative 111.1 newtons, and I have my vector arrow showing the direction there. So we need to take a look at the net force applied in the x direction. So pointing down the ramp, we have a force of 86.8 newtons, but we have a friction force of 57.7 newtons. So there will be a net force applied to the object. So in this situation, F net is going to be the sum of the forces in the x direction. Okay, so we're just going to add the forces up. This is going to be the x component of weight force plus the kinetic friction force. Now my weight force in the x direction is negative. Remember, the vector's pointing in a negative x direction. So negative 86.8 newtons plus our kinetic friction force, 57.7 newtons. So let's go ahead and calculate that. So our net force is equal to negative 29.09 newtons, okay? So our net force vector is pointing down the ramp. Let's put it in our column for answers over here, negative 29.09 newtons. Now in part G, it wants us to calculate the acceleration of the box down the ramp. According to Newton's second law of motion, we know that acceleration is directly proportional to the net force applied to the object, inversely proportional to the object's mass. So this is going to be negative 29.09 newtons divided by the mass, which is 14.4 kilograms. This is going to give me a negative 2.02. Now let's take a look at the unit value. In my numerator, I have units of newtons, and we know that a newton is a kilogram meter per second squared. So that's what I have in my numerator. In my denominator, I have units of kilograms, and algebraically, we can write this as kilograms over 1. So we're dividing fractions here. We can multiply by the inverse of the denominator, which will give me kilogram meters per second squared times the inverse of the denominator, 1 over kilogram. Boom, kilograms cancel. Look at that. Units of acceleration, meters per second squared, okay? Now, we can put this in the answer as negative 2.02 meters per second squared, or we can say the acceleration of the crate is 2.02 meters per second squared down the ramp, okay? So, negative 2.02 meters per second squared. So, my negative sign is showing the direction of acceleration, so it's going down the ramp, all right? In part H, it wants to know what the final velocity of the crate is when it reaches the bottom of the ramp. So, let me erase this here. And let me quickly draw another diagram. Okay, so we know that the displacement, let's say the crate starts right here. Okay, a worker places the crate there. The initial velocity is 0 meters per second. The crate accelerates down the ramp. We want to know what the final velocity of the crate is going to be. And the distance that the crate travels is 7.8 meters. So 7.8 meters. Okay? All right, so we're going to use the base equation. Final velocity squared is equal to initial velocity squared plus 2 times the object's acceleration times the object's displacement. Okay? Now, before we plug in any values, let's just go through here. Okay? My initial velocity squared. Well, looking at the diagram that we just drew, we know that the initial velocity is 0 meters per second. So this guy, he goes to 0. 0 squared, still 0. So we don't need to worry about this. Okay? So final velocity squared is equal to 2 times the object's acceleration. Now remember, acceleration is a vector, so we must show the appropriate direction. So negative 2.02 meters per second squared multiplied by the displacement of the object. Now remember, displacement is a vector as well. So we are sliding down the ramp. So this is a negative direction, so my displacement is negative 7.8 meters. So on our calculator, we're going to take the product of these values. And we get 31.512. And this is positive because we have a negative times a negative here. So final velocity squared is equal to 31.512. Let's take a look at our units here. I have meters per second squared times meters, and algebraically we can write that as meters over 1. So in my numerator, I have meters squared. In my denominator, I have seconds squared. Now we're not done here, because on the left-hand side of the equal sign, we have an exponent of 2. We have final velocity squared. Well, we have to get rid of the squared. And how we're going to do that is take the square root of that, because the square root will cancel the squared. But remember the old algebra rule that tells us to keep this equation balanced, what we do to one side, we have to do to the other side. So we're going to take the square root of both the left and right side of the equal sign. So what I have is final velocity is equal to the square root of 31.512, and this gives me 5.614. And we also have to take the square root of the unit value. So the square root of meters squared per second squared is meters per second. Okay? Remember that velocity is a vector, it's not a scalar, so we must show direction. So if our velocity vector is pointing this way, it's down the ramp, we need to indicate that. So we can say our final velocity is equal to 5.614 meters per second squared down the ramp, or we can simply put a negative sign on there. But to help describe it for this video, I'm just going to say down the ramp. And we can transfer this information to our column of answers that we've generated. So 5.614 meters per second down the ramp. Okay? So I hope this video has helped you calculate some of these values. I hope some of the diagrams have helped explain some things. But if you need any help at all, please send me an email or give me a phone call, and I will be more than happy to help you. I hope you have a wonderful day.